Good morning, everyone. Myself, Ashu Sharma, Assistant Professor, Department of Computer Science and Engineering, Nadia Institute of Engineering Technology and Management. Today, we will study unit number 5, image segmentation and representation. So, our topic is image segmentation and the briefing about how to proceed segmentation on an input image. So, let's start with what is segmentation. Segmentation divides an image into its constituent regions or objects. Level to which segmentation is carried out depends on problem being solved. Segmentation accuracy determines the eventual success or failure of comprised analysis procedure. As an input, we have an image, and as an output, we have constituent regions and objects. Basically, segmentation is a concept we can say which divides an image into regions of interest. Rather than focusing on entire image, we have to just focus on certain part of image of interest. So it will save the time and it will make that algorithm and program efficient enough for computerized analysis procedure. Here we have image segmentation algorithms that are based on one of the two basic properties of intensity values. First is discontinuity and second is similarity. When we talk about the discontinuity based approach, partition of image is based on abrupt changes in intensity, example age in an image. Discontinuity based approach, it means that there is a probability of discontinuity on an edge of an image. That is one of the techniques we use for segmentation and its algorithm. Similarity-based approach, image is partitioned into the regions that are similar according to set of predefined criteria. Methods of similarity-based approach is thresholding, region growing, region splitting, and merging. So these are the methods that we generally follow when we talk about the similarity-based approach. Now, in general, three types of discontinuities are detected in the digital images. The first one is the point, second is the line, and third is the age. So common way to detect discontinuity, run a mask, which is also considered as filter, you can say window or template, through the image like it done in spatial filter. So we have to use a mask and the dimension of mask is 3 by 3. So as per this given diagram, this is whole image. We take sub image in this and this is mask. Mask is of 3 by 3 dimension and its index starts from -1, -1, -1, 0, -1, 1 and so on till 1, 1. Now this is the center where index is 0, 0 and we take this pixel at position x, y in the sub-image. So we put this center over here at this position and then we apply this expression which is capital R equals to I equals to -1 to 1, j equals to -1 to 1, take summation and wij multiplication of x plus I, y plus k. So what we do, we just simply put this center w00 over here at this position x, y and then we just multiply each cell with respect to this mask cell. So then we take multiplication of all of these cells together and take sum of them to get this capital R. So here, the detection of discontinuity using this approach computes the sum of products of the coefficients with the gray levels contained in the region encompassed by the mask. The response of the mask at any point in the image is given by W1Z1 plus W2Z2 and so on up to W9Z9 because we take 3 by 3 dimension of the mask and the given sub-image. Here Zi is a gray level of the pixel which is associated with mask coefficient Wi. Response of the mask is defined with respect to its center location. So the With respect to its center location, response of the mask will be defined. Now for the point detection, we take this mask having -1, -1, -1 in 8 cells, and center is the sum of that. We take the mod of that, so it becomes +8. Isolated points in the given image can be detected by applying this mask. A point is said to be detected at the location at which mask is centered if mod of R is greater than equals to T, where T is a non-negative threshold and capital R is value calculated as per equation number 1 that we saw here in this slide. So this is the way. If this response capital R and take mod of that is greater than equals to capital T, which is non-negative threshold, then we say that a point is at location X and Y is detected. So T is user defined. User can define the value of threshold, which is non-negative. Now point detection mask calculates weighted difference between the center point and its neighbors. So uses the concept that an isolated point, a point whose gray level is significantly different from the background, will be quite different from its background, therefore can be easily detected by this mask. It means a point whose intensity is significantly different from the background intensity, it will quite different from the background, then it is easy to detect by using mask. Sum of the mask coefficient will be 0 in case of constant gray level area. If intensity value is common or constant, then you can say that the gray level area, then the sum of the mask coefficient will be 0. Now, this is for the line detection. These are 4 masks, and we have to apply all these masks horizontally, +45 degree, vertically, and -45 degree. These are the values: -1, -1, -1, 2, 2, 2, -1, -1. Then we take 45 degree anti-clockwise, it becomes -1, -1, 2, -1, 2, -1, 2, -1, -1. Then just we make sure that horizontal becomes vertical this way, and +45, which is anti-clockwise, it becomes clockwise -45 degree. So first mask will respond strongly. The first mask will respond strongly to lines 1 pixel thick oriented horizontally. So you can say this is dedicated for horizontal, where pixel is fine at horizontal alignment, and this is for that +45 degree. This is for vertical, and this is for -45 degree. So on an image, we have to apply all these 4 masks, and using this approach, the preferred direction of each mask is rated with a larger coefficient 2 in this case. So here we can see that 2 is that larger coefficient value in comparison with each cell value, which is -1. So here coefficients in each mask sum is equals to 0 in case of constant gray levels. Let we have R1, R2, R3, R4. These 4 masks are there. Response of first mask will be horizontal. Response of second mask, which is anti-clockwise +45 degree. Response of third mask, which is vertical, and response of fourth mask, which is clockwise and -45 degree. So assume that these 4 masks are run individually through an image. Here, if at a certain point in the image, Ri is greater than Rj, for all j not equals to I, that point is said to be more likely associated with a line in the direction of mask I. So we can say, if suppose R1 is greater than R2, it means that line is detected, that alignment towards horizontal rather than +55 degree. We can say if R3 is greater than R4, so we can say that point, that line is detected towards vertical rather than -45 degree. So here is the equality for all j not equals to I. That point is said to be more likely associated with a line in the direction of mass I. It means that point will be a point of horizontal line if R1 is greater than R2. So in this way, we have to apply all the 4 masks on an image and check what is exactly a point alignment with the line. If at a point in the image R1 is greater than Rj, where Rj is 2, 3, and 4, then point is said to be more likely associated with a horizontal line. This is the way we can detect alignment of a line and line detection. Sometimes we are interested in detecting all the lines in a specified direction. In that case, corresponding mask is run and absolute values of the result is threshold. The points that are left are the closest responses which corresponds closest to the direction defined by the mask. Now next is the edge detection. What is an edge? This is the most common approach for detecting discontinuity. An edge is a set of connected pixels that lie on boundary between two regions. A more reasonable definition of edge requires the ability to measure gray level transitions in a meaningful way. To get meaningful measurements of gray level transition, we consider idle digital image that give an edge and real ramp edge. So generally, when we talk about this diagram, for the leading edges, that first order derivative is positive, and for trailing edges, it is negative. And for second order derivative, there is a crossings, zero crossings also available. So this is the concept. You can say from brighter to darker, it is negative in first order derivative, and in second order derivative, but that steep peaks are there in second order derivative, so which is very sensitive. In first order derivative, we have gradient operators, and in second order derivative, we have Laplacian operators. So this is that example of an idle edge is a set of connected pixels in vertical direction here, and each of which is located at an orthogonal steps transition in gray level. This is the real ramp edge. In practice, due to the optic samples and other image acquisition imperfections edges are blurred. So this is the ramp light profile. Finally, the slope of the ramp is inversely proportional to the degree of the blurring in the edge. So thickness of the edge is determined by the length of the ramp as it transition from initial to final gray level. In practice, there is no thin path. Instead, any edge point now is a point contained in the ramp, and edge is a set of points that are connected. So these are the examples. This is the first order derivative, this is gradient, and this is the second order derivative, which is Laplacian. So this is that we have constant gradient is constant for points on the ramp and zero in area of constant gray levels, and second derivative negative at the transition associated with the light side of the edge, and positive at the transition associated with the dark side of the edge. So finally, magnitude of first derivative can be used to detect presence of an edge at that point in an image, and sign of the second derivative can be used to determine whether point is on the darker or lighter side of the edge. Second order derivative has two additional properties, produces two values for every edge in an image, positive and negative, and imaginary straight line joining the extreme positive and negative values would cross near the midpoint of the edge. Zero crossing properties. This property is useful for locating the center of edges. So this is for this session. Thank you very much. If I summarize, we saw what exactly the segmentation, which is the interest area in whole image. Rather than taking whole image, we had to take a specific part of the image for multiple level of segmentation. Then we saw point detection, line detection, and edge detection using edge detections using two derivatives, first order and second order. First order derivative was gradient, and second order derivative, which is very sensitive to edge discontinuity, was Laplacian. Thank you so much.